Hi everyone! Having now covered the aspects of two important families of engineering materials, metals to a great extent and to a lesser extent polymers, we are now ready to discuss composite materials. That is, the combination of two or more materials to form a new one. Combinations of different material families or classes are often realized to overcome the limitations of a singular choice, and over the next two lectures, we'll begin to examine some basic advantages of doing so and potential drawbacks. As good a place to start as any is with a very accessible composite material. Natural wood is comprised of three different types of polymeric materials. The long cellulose fibers are embedded in a matrix of lignin and a hemicellulose, or nearly cellulose. The orientation of the fibers in the wood create a grain, not grains in the context of metallic materials, but identifying a texture. That is, a unique orientation which there are observably different properties. Anisotropy. Natural wood is, in fact, a naturally occurring composite, and in this part of the lecture, we'll develop a framework of how to categorize and think about composites. We need to commence with a basic definition of a composite. At a high level, a composite is defined as a material where two physically distinct materials are combined to form a new one. By and large, they are comprised of two components, a material which is employed as a matrix and a material which is employed as a reinforcement. The term reinforcement implies that the sole purpose of the second component is purely for mechanical purposes, and this is not strictly true for all composites. This particular concept will be expanded on in the second part of this lecture. However, the use of the term reinforcement is prevalent and is perfectly valid when discussing mechanical properties, as we will in this part of the lecture. When it comes to engineering composites, the one that you're all most familiar with probably is colloquially known as carbon fiber. The correct descriptor for this material is carbon fiber reinforced polymer, and it describes it completely, a thermosetting polymeric matrix which is reinforced by carbon fiber. This carbon fiber is also a polymer, but having properties closer to a ceramic due to being completely made up of covalently bonded networks. Another example of a composite is aluminium silicon carbide, known colloquially as Al6. This composite has a matrix made up of aluminium, which is reinforced by silicon carbide particles. This composite employs a metallic matrix with a ceramic reinforcement. A more exotic example of a composite is a ceramic-ceramic composite, a glass matrix reinforced with a silicon carbide filament. Both this type of reinforcement and arrangement is also used in metallic matrix composites, replacing glass in the current example with titanium or aluminium. All three of these examples of engineering composites adhere to our basic definition. One material is used as a matrix and another as a reinforcement. They are all unique in terms of their structure and arrangement. The ratio of matrix to reinforcement, the scale, and the orientation of the reinforcement are all different. So too are the choices of what material is used for each role, and the overall costs associated with their fabrication, processing, performance and service, and final disposal or reuse. Let's now turn to the material families that can be employed and the underlying strategy for employing composites. In this course, the two classes of engineering materials that we have covered are metals and polymers, with more of a focus on metals than polymers. Comparing three main mechanical characteristics, they are quite different. The elastic modulus of metals is significantly higher than polymers and are much more resistant to fracture than polymers. And yes, the strength of metals is much, much greater than polymers, but both metals and polymers have significantly diminished strength when compared to ceramics. We haven't covered ceramics specifically in this course, but we have described material properties that can be attributed to them. For example, an extremely brittle steel can exhibit the same type of behavior as a ceramic. Generally speaking, ceramic materials have extremely high strength and moduli, but are equally extreme in their intolerance of any type of flaw, as characterized by having a lower fracture toughness than even polymeric materials. With these material classes available, the goal of a composite material becomes clear. By combining different classes of materials in differing amounts and arrangements, the goal is to create a material which takes advantage of the general properties attributed to each component. For example, carbon fiber reinforced polymer is a high strength, high fracture toughness, and stiff component. The contribution of carbon fiber to the polymer increases strength and modulus. Silicon carbide particulate reinforced aluminium, or Al6, is more apparent, acquiring the additional strength and moduli from the ceramic, whilst retaining the fracture toughness imparted by aluminium. In terms of combination options, the arrangement and form of the reinforcement within the matrix are quite varied. Choices between particulate or fiber can depend on the processing that's required for each, and the compatibility between the matrix and reinforcement is also a consideration. By and large, the strategy is to choose a matrix with a given set of properties and a reinforcement that exceeds these properties in some or more characteristics. The arrangement of the reinforcement in the matrix can operate on different length scales. While carbon fiber has diameters which are typically below 10 microns, silicon carbide monofilament is typically an order of magnitude greater than this. However, the arrangement can appear identical if the length scales are ignored. Ignoring the length scale of the reinforcement can potentially deny the ability to reinforce multiple directions for a given thickness of component. For example, aligning reinforcement orientations orthogonal to each other can change the anisotropy of the overall composite. However, such a strategy would not necessarily be able to be pursued with silicon carbide monofilament for the same thickness simply due to the size of the reinforcement. The same consideration can be applied to particulate reinforced composites. At what length scale does the presence of a particulate start to affect properties? Is an alloy a composite? We need to expand our definition of what a composite is beyond there simply being comprised of two things, one of which is construed as a matrix and one as a reinforcement. In deciding whether or not something is a composite, there are four characteristics to consider. First, that each of the constituents are chemically different. Next, when mixed, they stay separated. Their behavior must be such that the result behaves as one and will have appreciably different properties from constituents. We now have a definition of a composite which can extend over many length scales and successfully occludes alloys from being considered composites. While the result of an alloy is one that provides different properties than the constituents, and an alloy does behave singularly, the constituents do not stay separate. Let's now look at using the ways that the constituents stay separate as a further classification for the different types of composites that are possible. On a structural arrangement basis, there are three different types of composites. We've already seen examples of two of these types, particle and fiber. At higher length scales, there are also structural composites, which combine materials on a layer-wise arrangement. Subtending each of these categories, particle-reinforced composites can be further categorized by the size of particle that is employed. Fiber-reinforced are further classified by the continuity and alignment of the fibers. Structural composites are further categorized as laminates or panels. An example of the former is steel sheet sandwiching nylon to reduce vibration and noise transmission in automotive applications. As for an example of a panel, we'll come to that in a bit. Relatively speaking, particulate composites are fairly straightforward. Fiber reinforced, on the other hand, are a lot more complicated. Very different properties are achieved as a result of fiber continuity and alignment. For example, the continuity is an assessment of how long the fiber is, extending in some cases through the entire component, will have different properties as compared to reinforcement comprised of short, discontinuous fibers. If the fibers are aligned in one predominant direction versus randomly, this will also change the distribution of properties. As an example, body filler for automotive purposes is sold under two variants, short strand or long strand. The former is used for filling small bodywork defects, whilst the latter is used for structure or a foundation for short strand. Longer strands add strength, but cannot be finished smooth in the same way that short strand can be. Finally, if there is a preferred orientation to a fiber-reinforced composite, these can be combined layer-wise to form a structural composite panel. In this manner, one can navigate the varying length scales of reinforcement to determine what the component level effects will be. Let's now look at a comparison between properties of monolithic versus composite materials and why reinforcement directions matter. As described earlier, one strategy for formulating a viable composite is to use a matrix with relatively diminished properties compatible with a reinforcement with much higher properties. Here are some properties of thermosetting polymer compared against an engineering ceramic. The modulus of the ceramic is 2 orders of magnitude higher than the polymer, and the ultimate tensile strength a single order of magnitude higher. Comparing this ceramic against a low-carbon steel, it's clear that alumina is lighter and stiffer and offers a slight strength advantage, as long as you ignore that it has no ductility. Now, the combination of ceramic-like reinforcement to a high-strength polymer, as described by APC2, one achieves something that is 1/4 of the weight of steel and nearly 4 times as strong with comparable stiffness, at least in one orientation relative to loading. If the arrangement is as shown, then parallel to the loading orientation, the composite strategy is realized. However, in the perpendicular direction, it has the same properties as the matrix. Clearly, this highlights the level of anisotropy which could be characteristic of fiber-reinforced composites. As illustrated earlier, we can attempt to address this anisotropy by adding another layer to reinforce a direction lacking strength. However, what were to happen if we were to load this arrangement in pure shear? Yes, we could also align another layer in that orientation, etc., which is the strategy employed when deploying fiber-reinforced composites, but we may only do so if the loading is known and there is enough space to do so. Therefore, the significant drawback to composites is that they can attain exemplary properties, but only in certain directions. Let's now circle back to our first example of a composite, natural wood. One of the reasons why natural wood unto itself is often discounted as a composite is because other wood-based construction composites employ wood. The most prevalent is plywood. On the left, I'm showing a distressed piece of plywood as it demonstrates the various layers which are glued together with the grain of each layer orthogonal to each other. Repeated exposure to moisture has loaded the panel similar to being depicted in the center. Other examples of the use of wood's fibers to form a composite are shown on the right. Oriented strand board, OSB, is an example of a laminate. Wood chips and short wood strands are laminated together to form sheet, which can have similar properties to plywood. Medium density fiberboard, MDF otherwise known, is a common element in home furnishings and employs a significantly shorter strands of wood suspended in a polymer. This is where most get hung up on whether wood is a composite. If wood itself is a composite, how can it also formulate the core constituent of other types of composites? Well, we've already seen that composites can take on different structural manifestations, including composites being formulated from other composites. Natural wood is indeed a naturally occurring composite. The term wood fibers implies the structure comprised of cellulose, lignin, and hemicellulose, with the latter two to form a matrix reinforced by the former. To further verify wood being a composite, it can be deconstructed into matrix and reinforcement. Pyrolysis is a thermal conversion process where a material is heated in the absence of oxygen. Researchers have been able to convert natural wood by pyrolysis and additional chemical treatments into an inorganic arrangement as shown by this micrograph. After treatment, the cellulose is decomposed, leaving behind the matrix. Further chemical treatments at temperature can render this remaining matrix into a silicon carbide. and attempts have been made to cast aluminium into the free space to create a nature-derived engineering composite. If all this is possible, how can naturally occurring wood not be a composite? So that's it for this part of the lecture. Beyond determining categorically that wood is a composite, we've also established some ground rules for how to define and categorize composite materials. These ground rules are effective in describing composites as they are realized at all length scales. We've also determined that composite materials aspire to combine the best qualities of dissimilar materials by acting in combination. The degree to which this aspiration is met is countered by the inherent anisotropy which can manifest for many common composites, and clearly, if they are to be employed, specific attention needs to be paid to this aspect. Until next time.